Good morning, everyone, and welcome to the MOXXI webinar series. In our second webinar for the summer edition, I'm Sturgeon, and on behalf of the communications team, I welcome you to this series. So, a few words about today's speaker, Nick Everard. Nick Everard's mission is to measure the water in all the world's rivers, perhaps not all at once, but in time. Nick worked for over 30 years at the Environment Agency, where he gained experience in all things hydrometric and led on river discharge measurement techniques. Following his move to UK Centre for Ecology and Hydrology in 2020, Nick has been developing novel applications for drone and satellite remote sensing data, including the use of aerial drones, thermal cameras, and very high-resolution video from space for river flow monitoring. Nick is currently working on several projects, including a flood and drought research infrastructure catchment observatory project, in which he leads on river and precipitation monitoring and the tweed catchment, innovative use of drones with thermal and multispectral sensors for monitoring intermittent streams, remote control and autonomous systems for water quality monitoring, in situ data provision for Copernicus satellite services, informing World Meteorological Organization strategy for satellite remote sensing, and investigating the potential of air drones for river and floodplain flow monitoring. So a few words about our group. MOXXI Group is the working group under International Association of Hydrological Sciences that is tasked to promote the advancement of novel applications, novel observations, and techniques that lead to new sources of information to help better understand the hydrological cycle. It consists of an active community of over 140 scientists for more than 26 countries. Connections are made through newsletters, workshops, conferences, conference sessions, and hands-on field demonstrations at major scientific gatherings. I think we have time, so Professor Salvatore Manfreda, if he wants to say any more things about this group.
Thank you, Sergey. It's really a pleasure to see this initiative that stems from MOXXI working group. I think that is a great opportunity to promote the use of drones, camera system, satellites, and any advanced or innovative system for advancing hydrological observations that are still lacking in many areas of the world. We are working toward increase our knowledge about hydrology. So we promote the construction of a strong and international network of scientists, and we are succeeding in this identifying new path of research and new research line. I close my short intervention thanking the young students that organized these webinars, Nick Everard for joining the initiative, and also I warmly invite all participants to join the MOXXI working group through our webpage. Thank you.
Thank you very much. So now, so through this objective, we present the MOXXI webinar series today with the topic, the FluViSat satellite Velocimetry project, measuring streamflow from space. And we can, Nick, you can start.
Okay, thank you, Salvatore. Thank you, Sturgia. Wow, that introduction made my job sound really exciting and really cool. So yeah, I have to have to remember that one. Yeah, let me share my slides, and hopefully we can get started. Can somebody just let me know? They're looking okay? Give me a thumbs up or just say something.
Yeah, everything's fine.
Yeah, okay, cool. Yeah, so thanks. I have this habit of giving my talks a title and then I end up giving it a second title. So this is called Measuring River Flow with Satellite Video and Stills, because we actually did this slightly with still imagery as well as with video. The project is called the FluViSat project. And then I added this second one, the Resolution Revolution, because it sounds good, but we're trying really, what I'm interested in is trying to develop solutions with very high resolution satellites systems. So these are often commercial, but they offer very, very high resolution, sub-meter pixel sizes, and crucially rapid revisits as well. So this is the project. You can see the other project partners who are vital to the success of this project down at the bottom here. And I'll get cracking. So on that subject of resolution, if my slides will advance, here we go. Yeah, I mean, I just wanted to illustrate that before we get into the main body of the talk, really, that this is a still from one of the videos that we acquired, and we'll talk about how we got them and everything else in a minute. But yeah, just how high quality the imagery is that we can get from satellites now. And on this one, this is a frame from a still. We could see this truck moving down the road, and here's highlighted. We can see a little truck on the road in the satellite imagery. It's incredible. You could mistake this stuff for aerial imagery sometimes. So what we can do when we've got this kind of resolution is the thing. And we can also, perhaps with more hydrological relevance than the truck, we can see riffles. We can see roughness on the surface of the river pretty clearly within this imagery. Which is key really to what we're talking about here. So who am I? Sturgi's given you a very nice introduction, but just to remind you, my name is Nick Everard. I work at the UK Centre for Ecology and Hydrology, but I've spent more than 3.5 decades now, essentially looking for better ways to measure rivers. Whenever I'm given a challenge to do something, I'm always thinking, well, can we do this better? So that's what we're doing here. But I think really importantly, so I've only really been working at the Research Institute for about 5 years, but that's on top of more than 3 decades of making river discharge measurements with a whole suite of different tools, introducing new tools, developing methods and standards for their use, and so on. So I come with a really good grounding in understanding where and how to make measurements and why they're important and when and where they might work. So just to sort of guide you through, I don't know how many people on this call have made river flow measurements, but these are some of the techniques we used to use and one that we still do. So wading with a current meter, either with a rotating element, a little propeller, or more laterally, perhaps an acoustic one or an electromagnetic one. It's kind of time consuming. It's kind of boring. You get really cold, you get wet. It's, it was okay. It's necessary to do sometimes, but yeah, I've grown out of that. We used to do this. We used to hang current meters off a bridge on a sort of winch system with the big yellow sinker weight here to hold it down. This was kind of hazardous. We would do this from bridges where you were in danger of traffic running into you and maybe bumping someone on the head as you lower this 25 kilo weight off the bridge. So it wasn't great. It was also slow, time consuming. This is me as a boy hydrologist, stood on the front of the boat with a 7-meter long aluminium pole, which we had 5 of these current meters attached to that. And you might notice we've got a cable stretched all the way across the river. So we had to close this navigable river. We had to close that river to boat traffic whilst we did our measurements, which would take about 2 or 3 hours. So we weren't very popular with boat traffic. Also, you can imagine trying to hang on to 7 meters of pole in a flood condition. It was really quite dangerous. So I'm kind of proud to say that I led the introduction of ADCPs, acoustic Doppler current profilers, with a couple of colleagues, but I had a key role in that at the Environment Agency, and then developed a remote control boat. This is the smaller of the 2 remote control boats that we developed, but these are still in use. So generally, I think we would mostly consider ADCPs, acoustic Doppler current profilers, to be the reference for river flow measurement these days. And deployment with these remote control boats is a really effective and really efficient method of doing that. It's made things a lot quicker, a lot safer, and saves money for measuring authorities as well. So we still do that one. But yeah, this is a mock-up. This isn't a real picture. I mean, the flood is real, but that's a simulation of what would happen if we tried to put one of these boats into a major flood. And that's a kind of UK flood. That's somewhere in Scotland. But we would just basically be kissing goodbye to our equipment. It would get destroyed. We would lose it. So we need solutions. We need to measure these kind of conditions. So what can we do? And expanding upon that slightly, sorry. Yeah, monitoring networks. Globally, a lot of monitoring networks are in decline. Globally, a lot of monitoring networks are inadequate. But even where we've got good established networks, this is the UK. This is Storm Desmond, a big storm and flood that happened in 2015. There's a flow measurement station here, or rather there was. This is what remained of it after the flood had passed through. But the important thing to consider, aside from the destruction of the site, is what's it measuring? So the measuring section is between this little hut and these trees, but the flood has extended all over the floodplain. So there's a huge amount that's going unmeasured by this measurement station. This is another one. Whoever took the picture cropped it rather unfortunately, because what you can't see is that the measuring station was about to fall into the river. You can see it's no longer level, but it was about to fall in. It had to be demolished. And you can see enormous bank erosion on the far side of the river. So, you know, the established monitoring solutions are really struggling with major floods, I guess, is my message here. And how does that translate into something sort of quotable as a statistic? The UK Centre for Ecology and Hydrology, where I work, holds the National River Flow Archive, which is a sort of national archive, a repository of information on river discharge across. We have 4 nations that it holds data for in the UK. So there's England, Wales, Scotland, and Northern Ireland. And there's a total of about 950 stations in that data set. So I looked at that data set and I looked at what's the peak discharge that's reported for that gauging station. And then I compared it to the peak discharge that's been gauged or validated, in other words, manually checked by someone going out on site during that high flow and making an observation and proving that the numbers are correct. And what we find is that for about half of all of those stations, the peak discharge that's reported for that station is twice as big as the peak that's been validated. So in other words, if we think the peak flow for this river was 200 cubic meters a second, no measurement, no validation, no check has been made above 100 cubic meters per second. And then as we come along this graph, we find that for about 130 sites, it's 4 times as big. So if we think it was 400, again, we've never measured at more than 100. So the point here is there's going to be enormous uncertainty. And this, I should point out, it's important to point out, this isn't a criticism of the measuring authorities. I worked for one of them, so I understand. Measuring big floods is really difficult. It's difficult to get there in time. It can be unsafe. And as we've already seen, the measuring solutions that we've got historically can fail to operate in these conditions. So we're looking for solutions to that problem. And of course, the problem is almost certainly only going to get worse. I think it's fair to say that the majority of the images on this slide represent climate change intensified floods. They all happened last year. We can see Storm Boris in Europe. We can see Hurricane Helene in the USA, top right. We see a major tropical storm that hit in Asia, bottom left. And then we see the Valencia flood, bottom right, that I think we're all very familiar with. So how are we going to measure these things? We need to quantify the peak discharge to understand changes and forecast floods and try to defend against them. So the question we're posing here really is, we've got a problem. We know that our existing methods don't work. We know that monitoring networks globally in many places are inadequate. So the question is, what can we measure from space? Can we measure water from space? And of course, the answer is yes. You know, people have been doing this for quite some time. This graph here shows observations on the Congo River going back to 2002. So that's what, 23 years. I must admit, I didn't know about these kind of observations till relatively recently, but there's meaningful and credible looking data. This looks like good data to me, back to 2002. And I didn't attend this event, unfortunately, but the flyer for this event we're talking about 30 years of progress in radar altimetry. So basically what this is the use of satellite mounted radar to observe the water surface height. And it works on large rivers, has some uncertainty in it, but it's a pretty effective method. But look, there aren't very many points. And the other thing to note, the range of stage here is 4.5 meters. So, there probably is 0.5 meter, maybe more, of noise and uncertainty in these observations. On this scale of river, that becomes relatively insignificant, but it is there. But more worryingly, or more problematic perhaps, we've only got a small number of observations each year. So it's difficult to really build up a continuous picture. This river clearly has a kind of a real strong seasonality to it, but rivers that have less of a big seasonal variation are perhaps harder to monitor. Probably everyone on the call is aware of the SWOT mission. This is the Surface Water and Ocean Topography mission launched by NASA and with collaboration from the UK Space Agency and the French agency CNES. So what is this thing? It's a high resolution wide swath radar altimeter. So unlike the kind of point radar systems we looked at in the previous slide, this is giving us a big wide swath. It's a 10 meter resolution, but it's 120 kilometers wide. So that gives us the ability to observe many more water bodies. It also critically gives water surface slope, and I understand it gives pretty good water surface slope data. So the point here is it's getting us towards one of the critical parameters that we really need to understand river discharge, which is velocity. So it's been relatively simple to observe water surface height and water surface extent, but water velocity has been difficult, and that's what we are trying to address with the project that we're talking about here. So a bit more of this SWOT data. I put this in just because it looks so great, and I think it just shows you how impressive this system is. That the graduation in color that you see here represents relative water surface elevation. So we can see this incredible kind of smooth graduation from, I don't know which is lower elevation and higher. I guess this is higher elevation, the warmer colors, but the incredible detail you get from a single pass. It also has a nadir altimeter that gives you readings right in the center. Because of the nature of the instruments, there is an unmeasured bit either side of that nadir, but you get incredible data on either side. So an awesome system, but it still doesn't directly give us velocity. So this is the challenge. Rivers are flowing. When we look at those images that I showed you earlier on, the harm that we see, the destruction, the washing away of bridges, of buildings and so on, that's caused by water velocity. Discharge in rivers, the total volume, of course, is hugely dependent on the velocity. So we really need to know that flow speed. And here, a couple more illustrations of that. Water getting deep is very problematic, very unpleasant. Nobody wants it. But this is what happens when water also gets very fast. This is Hurricane Helene in North Carolina, in the USA last year. This is a before and after picture. So the force of the water, the speed of the water is unimaginable. I found some drone imagery and I tried to quantify. I got something like 7.5 meters a second from the drone imagery, but it was not shot for the purpose of observing water flow speed. So it was less than optimal, but 7, perhaps 8 meters a second. This is what happens. Buildings are washed away, infrastructure is washed away. Tragically, lives are lost as well. Another one from Helene, just to illustrate the incredible destructive power of fast flowing water. Anyway, so on to the science. That's the background, the science. So I think this is a video. Let's see, it is a video. So probably a lot of people on the call are familiar with video velocimetry, but it works really well with drones. So this is the principle that basically if we can see the flow of the water with our eyes, so can a camera, whether it's mounted on a drone or a bridge or a handheld phone, it can do that too. The beauty of using a drone is you can get it hovering above the river, so it gets a really great view of the river. And if you get a nadir view of you looking straight down, it's very easy to do the crucial thing of scaling the imagery so that we reduce uncertainty and error in the video by having this vertical view downwards. And so as you can see here, it's a slightly unusual velocity distribution, but it makes sense when you look at it. We've got these velocity vectors that represent relatively fast water on either side and slightly slower water in the middle, and then getting slower at the edges again. But we're tracking the movement of these visible features, in this case, these roughness and aerated features as they move downstream through this 20-second video. We generally use a 20-second video to do this. So moving this concept into space. And here's where we have to give credit to Mark Randall. So Mark is a hydrologist. Probably a lot of you know him. He works in Queensland, Australia. And he told me something like 7 years ago that he believed that we could do this video thing from space. And I tell it that I sort of fell on the floor in shock. And when I got up, I said, we need to do this. So more or less, that's what happened. It took us a couple of years to get this thing going. But what Mark became aware of was that a satellite operator called Planet Labs, who you may have heard of, they're an American company, but they have a whole constellation. They have 21 very high resolution satellites. They also have 200 lower resolution satellites that image the whole planet every day. But the SkySat satellite is their very high resolution satellite. And crucially, it can shoot video. So the SkySat can shoot 30 frame per second video. The resolution is 2560 by 1080. So it's, more or less equivalent to what you might get with a modern smartphone. So the question was, if we can do this thing with drones, observe the surface flow speed, can we do it with satellites? And so it was an exciting challenge. We were funded by the European Space Agency to try and find out. Project kicked off in 2022. And, without giving too much away, but probably giving it all away, this was one of the videos we got. This is the Indus River in Pakistan. You can see that it wanders a little bit. It sort of wobbles. It's not stabilized at this point. But crucially, you can see the flow of the water just like you can in the drone. So, it's tempting to say at this point, yes, our method works, because all we've got to do is apply the same processing, which is exactly what we did. But I think, for me, this is, I will say, one of the best videos we got. But if you look at this, you can so clearly, even though through the wandering, you can see the movement of these roughness features. So a critical consideration when targeting an acquisition with one of these satellites, and they are targeted acquisitions, they're tasked. So you find your location, you try and identify a time, and you request an acquisition, but you want to choose a place where you are going to see the surface flow. So you just coming into view, unfortunately, because we focused on this area where there were very clear visible features on the water surface, what you can't quite see is that if we'd acquired it about 1 kilometer further upstream, the method wouldn't have worked. 1 kilometer upstream, the river was much deeper, much wider, didn't have these roughness features, so it wouldn't have worked. So as with drone videos, where you choose to get your video is actually really important. So there you've seen the video. That's what we were working with. And here's what we got out of it. So we were able to apply exactly the same software to process these videos as we were using for drone videos. We applied exactly the same processing methodologies. And just as with drone videos, we didn't just get a single reading of velocity. We were getting multiple readings at each cross section. So in this case, from a single video, I was also able to do 3 cross sections. So we were able to validate in some places, but not everywhere. We didn't have the budget or the time to go out to Pakistan to try and validate this one. But those of you familiar with river discharge measurements will recognize that velocities ranging in this case from about 0 to 3.5 meters a second are what you would kind of expect in a high flow. But the fact we've got 15 velocity vectors across the river means that we can see a logical distribution. We can each of these are derived independently. So each of these is kind of a comparison and a validation of the one next to it. The fact that within the single frame of video, we could get 3 observations and they logically represent the distribution of velocity as we come around this bend, give us further confidence in this. But where we were able to validate, our results were almost all within about 5% of the reference values that we got with ADCPs. And we also validated with drones. So I think I'm going to show you a bit more on the validation in a minute. But for those who are not familiar, we used the space-time imaging velocimetry methodology for doing our surface velocimetry. So there are various different methodologies, the large-scale particle imaging, particle tracking. We used the STIV method because we felt that it was going to be most robust, given that we may not have the clearest traces or visible features to track. So the method, the way this works is, this is obviously, and really, it's great. More your here, English here, deal with. like a river. It had little white faces. You do these a lot of questions to learn. Honest, the video, it tracks variations in brightness moving along these lines. So you can see where these features move along the lines, you're going to get a brightness point moving along the lines. So it then, if I can get to my next slide, it divides these up. So it takes for each one of those lines, for each frame of the video, it kind of makes it almost like a little mini single pixel image, and it stacks them on top of one another. So as we can now break that down and see, here's our brightness feature in frame at time 1, at time 2, our brightness feature has moved slightly, at time 3 it's moved slightly. So when you stack these together, what you end up with is these diagonal lines, and you get multiple diagonal lines because multiple features move through those lines. So this represents just one of those, what we call search lines. So imagine this is just one of those lines, and it's divided up. One of these is produced for every frame of the video. They're stacked on top of one another, and you end up with this feature. Line running through the whole thing. That was actually this here. So I've simulated the position of these lines. We actually had a cableway across the river, and what you can see there is the position of the cableway. That the software also ignores that. It just looks at these features moving across the screen. Why do I have a pint of Guinness hidden behind the picture here? Because the more your river looks like Guinness, it's even better. So that kind of brown frothy beer, that's great. But in many parts of the UK, like Scotland, Yorkshire, we have this river, this water that looks like Guinness. It's peaty, comes off peaty landscapes, and it looks black. The water looks black, but it has white foam features on the surface, and that's really, really good for surface velocimetry. So yeah, look for beer in your rivers and you'll be happy, and then look for beer in the evening and you might also be happy. So yeah, so we've got these velocimetry, we've got these maps of water speed representing water surface speed. If we were in a classroom, I'd ask the question, does that represent discharge? And hopefully somebody clever would say, no, it doesn't. And that would be quite right. So to calculate discharge, which is of course what we're really interested in, we need the river's cross-sectional area. So where we were able to validate, and this was one of our validation sites, we took our ADCP, we took our remote control boat, and we got these cross sections. And you can see, hopefully, if anyone's familiar with ADCP data, you will recognize color represents water speed. So we've got this cross section. This shows us, the shape of this is the cross sectional area of the river. Color represents water speed. And you can see, as you might expect, towards the center of the river and towards the surface, the water is faster. And this is important because if we're only looking at the surface, we really need to know the relationship between the surface and what's happening deeper down in the water column. So we analyze our ADCP data using a piece of software, which you can see here. This is called QRevInt. So that stands for Q review, so discharge review. An international, INT stands for international. It was developed by Dave Mueller, who did work at the US Geological Survey, USGS, now has his own company called Genesis Hydrotech, I think they're called. And this software was developed whilst he was at USGS, but it's open source, it's freely available, you can get hold of it. But what it does a really, really nice job of showing us the velocity profile through our measured ADCP data, these dots, and then helping us to extrapolate to the surface and extrapolate to the bottom. So what we're really interested in here is the single value that represents the ratio of the surface velocity to the mean velocity in the water body. And we get that just by looking at the top here. And in this case, it's going to be, gosh, the numbers are a little bit small, but it bends back a bit. It's around about 0.7. So the water speed here is quite significantly faster at the surface than it is at the bottom. So we have to use this analysis to work out our velocity profile and apply what we call a surface alpha. It's basically a correction factor to make that surface velocity representative of what's happening underneath. So yeah, this cross-sectional thing. So we could only calculate discharge where we had a cross-section. So frustratingly, that fabulous velocimetry we did on the Indus River, we couldn't calculate discharge because we didn't have cross section. So I just wanted to put this out there as a sort of thought provoker. What if we had river bathymetry everywhere, or in way more places? So to illustrate that point, the Environment Agency in England has mapped the River Thames with a multi-beam sonar, which gives us this incredible detailed bathymetric map of the River Thames, not for the whole length of the river, because the navigation wasn't possible for the whole length of the river, but for the navigable reach, we've got this fabulous data. So to test this out, I took my drone to a couple of locations, and without knowing the cross section, I got my surface velocity video from the drone. I downloaded this data from online. I got my cross section, adjusting for water surface height on the day, and I calculated discharge, and it was within 5% of the nearby gauging station. So imagine globally, if we can start to make accessible either bathymetric surveys like this, or just discrete cross sections at key locations, we can start to get way more valuable observations from space and with drones. So many things we can do with drones are actually very much similar to what we could do with satellite, and the limitations and the things we need to enable are very, very similar as well. So working with drones is really good if you're also going to work with satellites. So now I've just got a couple of other examples of acquisitions that we got, just to show the variety and give you some more thoughts about where these methods might work and where they might not. I became aware that, unsurprisingly, there was a published paper that had looked at chunks of ice floating down rivers during the breakup season. And this published paper had looked at acquisitions that were from different satellites, so separated in time by, I think, tens of minutes, if not hours. But because the chunks of ice were so big, they could identify the individual chunks and see how far they'd moved. We had a slightly different approach. We recognized that ice chunks were going to make great tracers, but we applied the same technique of using video, and we got fabulous results. So there was a bit of a gamble going on here, because we had to wait. This is the Yukon River in Canada. We had to wait for it to break up, and then task and ask Planet to get us a video as soon as they could. But also, we needed clear skies. So luckily, these things came together. There was still a lot of ice floating down the river, and we got a clear sky. We chose a location where Environment Canada had a gauging station, so that we could compare results. And we got really nice results where the ice was present. But you can see where there was no ice, these gray vectors represent errors, where we couldn't derive velocity. On this side, there was a small amount of ice and slush moving down the river. So we got really good velocities across here, pretty good vectors, we think, on this side. When we compared, because they had a gauging station, I was able to get hold of an ADCP transect, which gave me the cross section. So I calculated discharge based upon this, using the velocity profile that was relevant for their previous ADCP measurement, calculated discharge, and we got 8,700. The gauging station was saying 8,500. So really quite close. We were pretty happy with that. But we couldn't get out there to validate. But because we chose a site where there was a gauging station with existing ADCP data, in other words, an existing cross-section and velocity profile, we could effectively do a sort of virtual calibration and validation. Just to illustrate another potential application of this kind of thing, which is, major disasters. We won't go into why this dam failed in Ukraine a couple of years ago, but it did, and it had disastrous consequences. We were able to acquire video. In the single frame of video, we could see both sides of the dam through which the water was pouring, and we were able to derive pretty good velocity vectors. Again, obviously, we couldn't get out to Ukraine and do validation out there on site, but we got some great vectors. And we were able to calculate what we felt the discharge was based upon what we knew the height of the dam was and the amount that the water had dropped, which gave us about 9,500 cubic meters per second. This is not the peak of this. We're going to talk about limitations of this method in a minute. It was about 6 days before there was clear sky to allow us to get an acquisition here. We requested tasking straight away, but it was 6 days before the satellite actually got a clear view because of cloud cover. So this was not the peak of this flood. I said in my title that we were using still frames as well. So we didn't do much on this. We weren't funded to do this. We just had access to some data, really purely to play about and see what we could do. So the SkySat has this rather complex method of acquiring data. It actually has 3 cameras, 3 imaging systems, and they're arrayed like this. So whilst it's taking this photograph with its forward-facing camera, it's also taking these two. So these were taken at the same time, but two of them are taken slightly behind another one. Why they chose to do that, I don't know. But it gives us some opportunities for doing velocimetry. So we found that Planet Labs are able to obtain imagery at 50 frames a second, still imagery. So question one, what's the difference between video at 30 frames a second and still frame at 50 frames a second? Well, it took me a while to understand, but really the difference is the satellite does not lock on to the AOI, the area of interest. So in video, the satellite adjusts its angle in space so the camera is looking continuously at your area of interest, say the white water here. With this acquisition mode, the satellite is simply just continuing looking straight down. It might be looking slightly to the side so it can see your AOI, but it does not lock on. So you end up imaging your location for a total of about maybe half a second, but the full width of the river is needed if you want to try velocimetry, which gives you a maximum separation time of 0.3 seconds. So what we were trying to do here was to see whether we could derive velocity from a pair of images with 0.3 seconds of time separation between them. If you think about it, where there's overlap between the image pair or between the cameras, we can potentially get a time separation of the image taken with this one versus this one. By the time this one passes over this area, the time separation is about 1 second. So we did experiment with that, but as you can see here, the overlap is narrow. So we didn't have that many where we actually hit successfully the best place for velocimetry is going to be this bit here. So in this case, we missed the best place for velocimetry, but it is another potential method of doing it. So how does this work? So hopefully Teams is going to be fast enough that you can see this, but this is a pair of frames. This is the Zambezi River below Victoria Falls. If you look at this pair of frames and I hop between them, I'm hoping you can see the movement. And that's what we're trying to track. So we had to rectify this imagery really, really precisely because the camera is moving overhead at, I think, 25,000 kilometers an hour. Its viewing position changes significantly, even within 0.3 of a second. So we had to rectify it. But once we've done that, what we're left with is hopefully riverbanks and surrounding landscape that stays still, but velocity in the river surface that moves. And then what can we do with that? So this is that same site. In this case, I got about a 1 kilometer reach of the river and was able to produce this velocity map. Again, we were not able to get out there and validate. I was not funded to do this research, so I didn't have a lot of time. It was just sort of fiddling around in the evenings and so on. But we got velocity vectors here, which represent quite logically. Here we're using FUDA LSPIV, by the way, not the STIV method, which gives us these 2D velocity vectors. But we can see the 2D velocity vectors match our perception of what's going on when we look at these pair of frames, and we get a logical and expected magnitude of velocity. We get velocities ranging from 0 is this kind of greeny blue color up to about 7 meters a second. Now these are major whitewater rapids that people raft, so we think 6-7 meters a second is probably quite realistic for those. So really keen to do more research on this. But yeah, why would we do this rather than video? Because it's way cheaper. Acquiring a video is more demanding of the satellite asset, whereas this is way less demanding of the satellite asset and therefore is cheaper and easier to acquire. Getting towards the end, another benefit, we talked about resolution, temporal resolution. There are 21 satellites in the SkySat constellation. I should qualify that by saying I think recent solar activity means there may be slightly fewer now, but there were 21. That means planet can image most parts of the planet, anything up to 12 times a day is what they claim. But to illustrate that they really can image multiple times a day, one of our sites was plagued by cloud. You can see here there's faint cloud in a couple of frames. They got 4 acquisitions within 24 hours of this place with this constellation. So the temporal resolution is a huge advance as well. Limitations, obviously we're really excited and really pleased with what we achieved here, but it's not perfect. The major limitation is cloud cover. If there is cloud cover, it doesn't work because it's optical. So the question is, can we resolve that? So we don't know at this stage, but we want to find out if we can use synthetic aperture radar. So ISI is one of 3 or more operators who have constellations of very high resolution synthetic aperture radar or SAR satellites, they're able to acquire video with the SAR satellites. In this video, this is an example they have on their website, and they shared with me. You can see the movement of waves breaking on the ocean shore. You can see patterns behind boats. So can we derive velocity in rivers? We don't know at this stage, but it's really exciting to think that we might be able to. And I kind of suspect we will be able to. So getting really close to the end now, this satellite radar altimetry thing, there are a lot of observation points, virtual stations around the world, about 10,000 or more, but most of these have no bathymetric data. So just coming back to this thinking about what could we do if as a community we could find a way to realize bathymetric data. We could improve observations globally enormously if we could get bathymetry, and then if we could add velocimetry to some of these points. Maybe not every time, you know, most gauging stations work on a basis of measuring water stage, water surface height, water depth, because it's easy, and then using periodic measurements of velocity through gauging to relate that into and build up a stage discharge relationship. So maybe periodic velocity readings combined with bathymetry can turn these into something that is rather more precise measurement of global discharge in rivers. So now the outlook, I think the potential for wholly remotely sensed river discharge monitoring is very close. There's huge potential for data sparse areas such as Africa, Arctic rivers, etc. Probably less pressing demand and perhaps less potential in Europe and other densely monitored locations. Very low latency, very rapid repeat observations are now possible. So in other words, you know, observing the buildup of a flood event is now possible. Observing that, you know, the full flood event with observations every few hours is possible. So I think this is just the start of what we can do in these kind of areas. So future research ideas and objectives, river cross sections. I would love to see the development of global database, optical satellite video, refining workflows. The workflows that we had weren't super fast. You know, it took us a few days to get the videos rectified and processed, but obviously that could all be improved. Exploring the potential of synthetic aperture radar, really keen to do that. But then combining very high resolution optical with AI for river discharge. There's lots of other very high res data out there. And I think there's lots we could do with, for example, AI to get data from that. If you're interested in, you know, still have any interest in this project after I finish my presentation, we have a preprint out. The paper is in review at the moment. Hopefully it'll be published fairly soon. I think you can find this QR code and the link in the chat. But if you're quick, you can grab a snap of it there. But if you search measuring the world's rivers with videos, I think you'll probably find it anyway, especially if you add my name, then you'll find it on ResearchGate and elsewhere. So yeah, that brings us to the end, and I'll invite any questions. And just for fun, this was an acquisition where we actually got the satellite acquisition at exactly the same time as our friends at NVE in Norway were making a measurement of river discharge. And you can see their boat in the video. You can see the boat moving slowly across the river in the video. So we're really excited by that. And that's it. I'll invite questions.
Thank you, Nick, for this wonderful presentation. We can move on to the questions. Please write your questions in the chat so I can read them to Nick and he can answer them. In the meantime, I'll read some questions that have been already written in the Google form for the registration. Yes.
I just a comment. I would like to, Sergio, sorry for the interruption. Yes, I would like to hear the question from the participants, but I have to thank Nick for his enthusiasm. That is contagious, and I think this is what we want in MOXXI, and it is extremely nice and beautiful to hear his presentation and the pleasure of making research and investigation and exploring the potential of innovation in this field. Thank you so much.
Thank you, Salvatore. Very kind. But come on, someone must have a question.
So the first question I will read from the Google form. How do you deal with the challenges of getting a decent cross section for these locations?
Yeah, I think we've talked quite a lot about that. It is a challenge. I mean, for where we were able to validate, so with Mark being in Australia and me being based in the UK, we got acquisitions for sites in the UK and in Australia, and we made sure they were sites where we could get cross sections with our ADCPs. So that's how we did that. But yeah, I think, you know, that we've discussed that, you know, perhaps quite quite some detail, that there is a need, I think, to try to develop a global database of cross sections to enable this stuff. So I don't know if any monitoring authorities currently publish online their river cross section data. I think perhaps USGS does some of this. The Environment Agency, as I showed you, has published as open data its river survey data, but that's obtained. That's not the hydrometric data. That's not derived, you know, intended for river discharge measurement. So I think where we stand today, there are hundreds of thousands, probably millions, of river cross sections in ADCP data sets all around the world. And if we could find a way to dig those cross sections out, precisely relate them to river surface height, you know, to the stage at the time they were obtained, you know, then it would be really powerful to develop a global database of those river cross sections. I hope that's kind of useful as an explanation, but I think it is a challenge, and it's one I think we should address as a community.
So another question from Google form. Are there any platforms Africa can use for this type of data, especially because there's very limited on-ground data for validation purposes?
So specifically Africa, was that, Sturgia?
Yeah, it was just for Africa.
Yeah, no, I think there is huge potential. I think that if there's one continent where these methods have the greatest potential to be valuable and to work, I think it's Africa. I think the challenge is, you know, this was a proof of concept research project. So I think we've proved that it can work. I think the challenge is funding it and trying to make it operational. So I've been building relationships with WMO and trying to build a relationship with the UN. But yeah, I think there is huge potential for Africa. It would be great to develop something that we could kind of make operational. But at the moment, these videos do cost money. They cost a four-figure sum, shall we say. We got a discounted rate, but you know, they're going to cost a few €1,000s to acquire. But I think, which seems expensive, but if you think of the cost of mobilizing an observation team to go and make measurements in remote areas, it can cost you more than that. You know, Environment Canada made the comment that putting two people in an aircraft and sending them to make a measurement on the Yukon costs more than acquiring a video from Planet Labs. So, you know, there is that kind of thing. Also, I suppose if more videos are required, the price may come down. So I think, yeah, huge potential for Africa. The main barrier probably is finding a way to operationalize a method that's based upon commercial data. And I'm really keen to try to address that. I want to work with the commercial sector. They have the highest resolution satellites. They have the best revisit times. So finding a way to enable that working is something I'm trying to pursue. I think we have got a couple of questions in the chat right now, haven't we? From the
Yeah,
live.
we have some great questions. So the first one, what would be the minimum river cross section width using the currently available images or video resolution?
Yeah, it's a good question. For the narrowest we obtained for this research was the Zambezi below Victoria Falls, which was about 50 meters wide, but it had very big roughness features. It had those big white water features. So at the moment, I think about 40 or 50 meters, but the satellite resolution improves all the time. One important consideration is not many providers do video. The SkySats are quite old. Planet Labs are launching a new constellation, but we don't really know if the new constellation is going to do video. So, you know, part of the reason for promoting this work is to try to convince the satellite providers that there is a market for video, to make sure it's a capability that isn't lost. But yeah, I think currently 40 to 50 meters with better resolution. You know, Airbus is doing 15 centimeter super resolution with their Pleiad Neo satellite. Doesn't do video, but it could. You know, you could theoretically do video with a satellite like that.
Great. So next question from Annette Eldner. Hey, Nick, thank you for this very nice presentation. Great to see where Velocimeter has gone to. Do you see any chance it might be usable also for smaller rivers at some point? And did you also evaluate options to get the water level from satellite to eventually get to the discharge?
Yeah, I think we just covered the first part of the question, so I'll go on to the second one. Yeah, we kind of did, but I think at one or two of the locations, so in Pakistan, we had fabulous videos, but we had no on the ground validation. The nearest flow measurement stations were about 100 kilometers upstream and downstream, and there were tributaries coming in and out and so on. But we found that because of the nature of the terrain surrounding the river, we could see exposed kind of beach areas and inclined rocks. So we couldn't, from the satellite imagery, quantify precisely the change in elevation, but we could see relative changes in water surface height. But I think, you know, I have a slide that I show in another presentation, which is Airbus Pleiad Neo imagery. And in it, you can see the Eiffel Tower. It's a central Paris. But next to it, you can see the road markings. And you can see the road markings so clearly that it got me thinking, well, if we were to build a large inclined gauge board, stage board, put it in the river, we could read it with the satellite imagery, because the satellite imagery is so clear. So we didn't really get very far with it in this case, but I think there is potential to do so in the future, particularly as resolutions improve. And we could link it to, of course, radar altimetry would be the other way to do it. You know, a hybrid solution, I think, between radar and optical.
Great. So next question from Francesco Alonghi. You mentioned,
I think we already covered that. That's river width again. So if you're happy, Francesco, I think we've covered that.
Yeah, that's true. Maybe you can answer questions from Ollie Swinstone. You mentioned using SAR systems in the future for velocimetry. What methods are you considering to calculate this?
Yeah, okay. So at the moment we kind of don't know. But I'm not a SAR expert, but I've been speaking to ICEYE in particular, who operate a whole constellation of SAR satellites. They're interested and excited, so it can't be a completely so the relative motion of the train compared to the direction of the SAR satellite, but it will appear displaced. So the question then is, if your water's flowing fast enough, would it appear displaced from the river channel? And we don't know. And there are could we get a Doppler shift from the SAR signal? Again, we don't really know. So yeah, I think that we don't really know, but I think there are 2 or 3 different possibilities using SAR that we want to explore. The next question, I guess I could just read. Are we considering EO and aerial drone synergies to cross-validate future measurements? Yeah, absolutely. So I don't know if I mentioned it. I don't think I did, but where we did validate, we validated by comparing with ADCP data, but we also flew drones. So we were able to do a direct comparison of surface velocity derived from satellite and surface velocity derived from exactly the same processing software from a drone. So, but yeah, I think you can now, drones are very, very low cost, very easy to deploy. You can buy drones that live in a box on site and pop out when you want them to. So the potential for using drones for validation is huge. And again, a really fun thing to explore. Gosh, Ollie's put a lot of questions in here. Do we have too many other questions to? Perhaps we should move on to someone else's questions so we can cover, because I do have to go at 11, I'm afraid. So what should we do next?
I think we have to stick to the plan and try to close the session in an hour as promised. So I would pick just one last question if possible.
Well, let's go with the one that's central in my screen at the moment, and that we haven't really touched on, which is would the turbidity and high sediment flow affect the measurement technique? It shouldn't really, and turbidity I think could give us something else to work with. Legleiter and Kinzel, I hope I've got the names correct, published something looking at satellite video for velocimetry, the same kind of approach that we took. I think in the river they chose, they didn't perhaps have the surface roughness features that we had, but I think they were able to see variations in turbidity in the sediment-laden river. So I think there's potentially the sediment loading could help us. And we're also interested, multispectral maybe would help with that. I don't know, or hyperspectral. We're also looking at thermal imaging for these kind of things. So I think turbidity, could help. I don't think it's ever going to hinder. I think it could help potentially. And there we should probably wrap it up, I should think.
Yeah, that's right. Thank you very much for the great presentation and discussion today. Thank you everyone for coming. Yeah, don't forget to attend our next webinar on the 10th of September with Sefedi and Joma. It's the third webinar of the summer edition series, and also many more monthly webinars to come in the future, so stay tuned for that also. Also, don't forget to share, to follow our page on LinkedIn for all updates and register for the upcoming webinar. You will find the link in our LinkedIn page. And thank you everyone for joining.
Okay, thank you. Thank you, Nick. Thank you everyone for participating.
Bye. Thank you everyone.
Thanks for inviting me. Thanks for the opportunity. It was great. Right. See you all.
Absolutely. We had a lot of participants, so it was a very successful event. Thank you.
All right. Thanks. Bye.
Bye.